typically when I see sine or cosine, and this is true both in 21C and in 21A, when I'm thinking about sine or cosine and I know we're going to infinity, like with a series or like with a limit in 21A, I'm usually thinking about cosine or sine being in between -1 and 1. So I would probably start this by saying, well, I don't know what cosine does. I mean, I know that cosine does this, right, as we go out, but I know that cosine of anything is always between 1 and -1. And then I can manipulate this to look like that. I can add 1. And I can divide everything by n. So that, oh, sorry, I could divide everything by n, but I want to divide everything by n squared. So this is 0. So 0 is less than or equal to the thing we're interested in. And that's less than or equal to 2 over n squared. But we know that the series for 2 over n squared definitely converges, right? The sum from n equals 1 to infinity of 2 over n squared converges. And so since the sequence of the series we want to know about is less than the sequence of the known convergent series, we can say that by direct comparison, this series has to converge. Because its terms are both less than the terms of the other series that's convergent, and they're also positive, right? You have to be positive. Julian, I think I just did the question you had asked about. Sorry if I got there a little ahead of time. I was just showing how the problem, oh, sorry, for those of you that I think said for all of you, this was problem number 20, I think, from section 10.4 in the textbook. I have to double check. Yeah, 20 from 10.4. So we showed it converge by showing that this sequence is less than a sequence of a convergent series. And again, the impetus for this was that whenever I see a series, an infinite series that involves cosine or sine, it's not always true, but it is often true that it's useful to remember that cosine or sine is between -1 and 1. So this converges. Cool. All right, now for this other question that somebody sent me that looks complicated. This was from someone's homework, which is fine. It's a little bit lengthy, so I wrote out some stuff. So the question was to approximate the infinite sum from n equals 1 to infinity of 4 over n squared with a partial sum, which I wrote over here. You don't really need this, but I wrote it anyways. Sorry, the partial sum is the first capital N terms. So the question is really, what does capital N need to be so that our estimate is within 1/10,000th or 10 to the -4 of the actual value? And specifically, this problem says to bound the error using the integral remainder estimate, which I then had to look up because I didn't remember what it was. So the integral remainder estimate, Rn, which is always so R sub n is always the way we write the remainder after the first n terms. So, right, Rn is the actual sum minus Sn, or as I like to write it out, if I'm writing out the actual sum, right, it's the first, A1 plus A2 plus dot plus A sub capital N plus A sub capital N plus 1 plus dot forever. The first capital N terms is the nth partial sum, and then everything after that, and you can definitely watch the video later when I post it, Julian, if you need to go back and look at it. Everything after that, that's your remainder after the first n terms. So this is our approximation, and the remainder, which we usually don't know exactly what it is how much we're off by. So we're going to approximate this remainder. Now there's a few different ways of approximating the remainder. One of them we'll talk about later on. But this one was in the, I was like, where do you even find this test? It's in this test, the section, I think it's in 10.2, the section that has the interval test in it. So the interval remainder estimate says that your remainder is between the integral from n to infinity of your function and the integral from, oh, sorry, this should be an n plus 1, sorry. The integral from n plus 1 to infinity of your function and the integral from n to infinity of your function. Specifically, your remainder is less than, so bounded by, the integral from n to infinity of f of x dx. So the question is, how big does n have to be? What does this actually need to be so that our remainder, which is less than this, is less than 1/10,000? So all of this work to do the following, I mean, it was not really anything really, I just wrote down a bunch of words. So what we really want to do is we want to say, okay, what does n need to be so that the integral from n to infinity of our function, which is 4 over, we're not going to write lowercase n, we're going to write x instead. So the integral of 4 over x squared dx is less than 1 over 10,000. That is the question we are trying to answer. Right, this is our, I should say, right? So we're saying that we know that our remainder is less than this, and this is less than that. That's the whole idea, I guess less than. Okay, I think I can write some of this down here. By the way, Julian, I know you had also said in your reflection something about hyperbolic trig functions. I wasn't exactly sure what you wanted to know about, so feel free to shoot me a message or a chat, whatever, and I will try to address that if you let me know. Okay, so this isn't too terrible. I'm going to do this integral. It's obviously improper. So this is going to be the limit as b goes to infinity of the integral from n to b. I'm going to rewrite 4 over x squared as 4 times x to the minus second dx. And then I'm just going to calculate this. It's going to equal the limit as b goes to infinity. I will say usually in 21C people get a little more loosey-goosey with writing these limits. Like you could probably just actually do the integral and plug in infinity and say that that part's going to be 0. I'm trying to be precise because that's what we're supposed to do. Integrate this, you get 4x to the minus 1 over minus 1. Let's rewrite that as negative 4 over x. From n to b, again, we're trying to find this capital N. So that's going to be the limit as b goes to infinity of negative 4 over b minus negative 4 over n. Clearly, this part's going to go to 0. So we're left with capital 4 over n, capital N, capital 4. I don't think there's capital numbers, sorry. Although I've definitely had the discussion before, people is, what if there was lowercase and capital numbers? What would it look like? I don't know. We never figured out a good answer. But we want this to be less than 1 over 10,000. So that's the idea. You take your integral from n to infinity, which is a bound for your remainder of the nth partial sum, and then you set that to be less than what the bound was they wanted to find. I think this one works out perfectly. This is going to be, so I'm going to cross multiply. I'm going to get 40,000 is less than n. So I believe, and this is where you have to be careful here, you either have to put your, because I think n has to be strictly greater than this, right? Because we want our remainder, which is less than or equal to this, to be less than 1 over 10,000. So since we want to pick an n, so that this is actually less than and not equal to 1 over 10,000, I think we have to go to 40,001. I would try 40. So if you're doing this problem, I forget who asked this, but if this is your problem, I would, if you're getting n strictly greater than this, I would first try an n equal to 40,001. And then if that wasn't right, I would try 40,000. It should be one of those two. Sometimes it can be a little picky as far as what they want, but that is the idea there, is that you want to get one of those. All right, we'll circle back around maybe today, maybe Thursday with more remainder estimates. It's always kind of a, because again, you're right, we're trying to see like, so what we've said with this is that if you take, that's a good question. Yeah, I'm always, so if you do the partials, if you add up the first 40,000 terms, your partial sum will be very close to the actual sum. How close? Within 1/10,000. And now I'm not 100% sure it's the first 40,000 terms or the first 40,001 terms. Yeah, it's probably 40,000, but yeah, things, it's always a little bit like, yeah. I'll try and get that nailed down a little bit better for next time. But it's always kind of a little dicey. All right, so where was I going next? I think. So last time we had talked about alternating series tests. We had kind of ended talking about the difference between absolute and the other conditional convergence. I feel like it might be good to say a couple more things about that and then to move on to talking about power series and interval/radius of convergence. And actually, this conditional convergence thing definitely comes up when you're talking about the radius and interval of convergence, so it is worthwhile. So just a couple more examples, like for example, this series, the sum from n equals 1 to infinity of -1 to the n plus 1 times n over n to the 4th plus 1. Here's what I want to kind of help you avoid. I want to help you avoid jumping to the alternating series test if you don't have to use it, right? You could totally show that this series converges by the alternating series test. I'm not going to, but I'm just going to tell you this series definitely does converge by the alternating series test. Because one, gosh, I can remember, like there's three things. What are they? Because one, the terms are positive, right? That's one of the conditions. Two, the limit of them is 0, clearly. And most importantly, the terms are decreasing. It's not 100% easy for this one, but it's pretty easy to show that, oh yeah, if the next term is definitely going to be smaller than the previous term. And here I can justify that without writing that by saying, well, yeah, if I let n get 1 bigger, the top is only going to get 1 bigger, but the denominator is going to get a lot bigger because you're going to add 1 to n and raise to the 4th power. So yeah, definitely decreasing. You could either show that by showing that the derivative is negative, right? That's usually the easiest way. You could totally do that here. You can show that f of x equal to x over x to the 4th plus 1. If you check the derivative, it was negative. However, that's way too much work for this one. And the reason it's way too much work is, although you could show it converges this way, you could also just show that it converges absolutely. So typically, if I am asked about something and I see that it's alternating, or even more generally, not always positive, right? There are terms here that are going back and forth between positive and negative when you count this in here. I'm going to always at least think about trying the absolute convergence test first. So does this series, which I know feels silly to write out, the absolute value of -1 to the n plus 1 times n over n to the 4th plus 1. Really, you should just say this series is just the same as this without the absolute, the -1 to the n plus 1. Does this series, which is this series, does this converge? Well, yeah, this converges. This converges by, I would probably use limit comparison because I'm lazy, but you could also use direct comparison, right? This is less than n over n to the 4th, which is 1 over n cubed. So yes, this converges by direct comparison or limit comparison. Direct comparison with this series. Right? These terms, which have a bigger denominator, are less than these terms. Since this series is convergent, this series also is convergent. So then here's what we get to say. This series converges, which means this series converges absolutely, which means it converges. So if something converges absolutely, that automatically implies that it converges. So this being absolutely convergent means it's convergent. And I think personally, it's way easier to show that this series, not this series, but that this series converges by comparison, either direct or limit, than it is to show all these things, specifically this last thing here. Also, usually if someone's asking you about if an alternating series is convergent, they're almost always going to ask you if it is absolutely, conditionally, or neither. So if someone's asking about this, they're going to say, is it absolutely convergent? You need to check that, which we checked it is. And then if it's not, then you have to check if it's conditionally convergent. And then if it's not, then it's probably divergent. So here's an example. Again, I will point out there are some series that we are not able to determine their convergence. They're just beyond the scope of this class. That's fine. I forget what the famous one is, but there's definitely a pretty famous one that requires something called the Dirichlet test, which we don't learn in this class. It's definitely upper division, like I think it's something you learn when you take like the 127 series. Anyway, where'd you go? So let's look at this example. The sum from n equals 1 to infinity of -1 to the n times the square root of n over n squared plus n squared. Sorry, let me think for 1 sec. N, let's do n. Oh, not n to the n. N. Okay. So is this absolute or conditionally convergent? Or neither, I guess, right? Neither technically could be an option. If it's neither, well, yeah. So is it absolutely convergent? Well, I'm going to look at the absolute value. So when I'm looking for absolute value convergent, if I'm looking for absolutely convergent, if I see that, right, if I see that without this, the terms are just positive, I'm just going to write it as this. Right, I know I'm taking the absolute value of this, that's just getting rid of the alternating part. Okay, does this converge? No. This does not converge. Because if I use the ratio test, for example, not the ratio test, the limit comparison test. If I limit compare it with just the square root of n over n, which is equal to 1 over the square root of n, that's divergent by the p-series test. And if I do the limit comparison, the limit is n goes to infinity of this one over this one, square root of n over n plus 1 over 1 over root n. If I simplify this, I'm going to flip and multiply. I'm going to the limit as n goes to infinity of n over n plus 1, which is 1. The limit is not 0 and not infinity, which means that this and this do the same thing, but this diverges, so this diverges. So it is not absolutely convergent. It could still be conditionally convergent. So if you try to see if something's absolutely convergent and you get the answer that it is not, then you should go to the alternating series test if it's an alternating series. So then I would do the alternating series test. So one, I almost don't even check the first thing usually. Obviously, the non-alternating part, square root of n over n plus 1 is clearly greater than 0. 2, clearly the limit as n goes to infinity of the square root of n over n plus 1 is equal to 0. You could use L'Hopital's rule, but I'm just using the fact that the degree on top is less than the degree on the bottom. Right? N to the 1/2 on top, n to the 1 on the bottom. And so then the only thing we have to check is that it's decreasing. And for here especially, I would definitely use the derivative. So my function is the square root of x over x plus 1. So the derivative is going to be the bottom times the derivative of the top, which is 1 over 2 root x, minus the top times the derivative of the bottom, which is 1, all over the bottom squared. So almost every time when you do this decreasing thing, you're going to have a quotient rule because almost always we're using a quotient. And the denominator is always going to be squared, which means the denominator is always positive, which means it's not going to contribute to whether or not the derivative is positive or negative. So typically after this, if I'm trying to say this is less than 0, I jump straight to just saying the top part's less than 0, which I guess I'm going to have to write up here. So I'm left with x plus 1 times 1 over 2 root x minus the square root of x being less than 0. And I guess I would factor out a 1 over root x. So I'm left with 1 over root x times x plus 1 over 2. So x over 2 plus 1/2 minus x. And that's equal to 1 over root x. This is a 2x over 2. I guess I should have factored out a 2 in the denominator as well. So I'm left with x plus 1 minus 2x. So that's going to be 1 minus x. And that's definitely negative if x is greater than 1. Which means that this is negative as long as x is bigger than 1. Great. So we showed the things. We showed that the non-alternating part was always positive. We showed that the limit, or we observed that the limit was 0. And we did show that this function is definitely decreasing as long as n is bigger than 1, which that's perfectly fine. It has to be decreasing after some point. So this is conditionally convergent. This is conditionally convergent. It does converge, but it does not absolutely converge. All right. And I think I could do more examples like that, but we're gonna kind of come back to that later on. There is this kind of cool example, but I don't think it's that important. So I'm just going to say a thing, and then if we care about it later, you guys can kind of let me know. But it is true that series that are conditionally convergent, meaning alternating series that converge but are not absolutely convergent, a conditionally convergent series can be arranged to add up to any number. Let me just show you this. So it's not really that important with this class, but it does have kind of a, it's just kind of an interesting fact. So here is a quick example that I will not write down. I'll just kind of walk you all through real quickly. And then if you really care later on, it's definitely more of an upper division / graduate level math kind of concept, but doesn't mean you aren't prepared to see it right now. So here's an example. Conditionally convergent series can be arranged to sum to any number, including infinity. So here is the most famous example of a conditionally convergent series, the alternating harmonic series, 1 minus 1/2 plus 1/3 minus 1/4, et cetera, et cetera, et cetera. And if you add all of these up in this order, it does add up to natural log of 2, which is somewhat challenging to show, but is not the point. On the other hand, we can rearrange this, right? We have an infinite number of terms. We can write them any way we want. So here's the way that Grant has decided to rearrange this. I'm going to add the first so many terms. So 1 plus 1/3 plus 1/5 plus 1/2 plus, and he's going to stop when he gets to just over, looks like 10 terms. Or maybe no, he's getting to when the value is 10. So he's got 10, and then he's got minus 1/2, and then he's got the next 10 minus 1/4, and then the next 10 minus the next like 1/8 or 1/6. And so basically, yeah, that's interesting. You can make a sum equal to 10 or to any number. I feel like 10. Oh, I see. Interesting. Yeah, anyway, this is not that important. I feel like I'm not doing an excellent job of describing it, but you can rearrange the numbers so that you can get kind of anything you want, which is interesting, kind of, not that important, really, not that important in this class. So yeah, I feel like maybe I just wasted a minute of your life, but okay, well, we'll live. Let's move on to talking about power series and interval of convergence. Okay. So what is a power series? Well, a power series is a series where you've got some variables. I mean, that's a very not technical way of saying it, but that's kind of the idea. So let's look at a few examples that will kind of build us up to a power series. So let's look back at some geometric things for 1 second. There was one that I had in mind just a minute ago that seemed really worthwhile for a reason. Oh well. Anyway, sorry. So let's say, oh, I know what it was. I'm gonna kind of bring in an extra example here. I know we didn't do any of these, I think, but sometimes teachers will ask you to write a repeating decimal as a what's the how yeah, oh yeah, I think it's to write a repeating decimal as a fraction. So for example, what if I wanted to write the repeating decimal 0.262626 as a fraction? There is a very kind of slick way of doing this, and it involves using a geometric series. So I could write this as 26 over 100 plus 26 over 100 times another 100, right? Right. This is 0.26 plus 0.0026 plus 0.00026. Each next term is 1/100th of the previous term. So you might recognize here that the ratio is 1/100th. Every term is the previous term times 1/100th. Well, we know how to add up a geometric series where the ratio is less than 1. This is equal to the first term over 1 minus the ratio. There's the first term over 1 minus your ratio, which is 1/100th. This is equal to 26 over 100 over 99 over 100, which is 26 over 99. So that's kind of neat. You can take any repeating decimal with however many decimals that repeat you want and always write it as a fraction using the fact that we know how the geometric series always sums. So kind of cool. Kind of. So that's kind of the idea, right? And we could, I mean, it doesn't have to be something like this. You could also just add up terms like, what if we had, 8 minus 4 plus 2 minus 1 plus a half minus a third, a fourth, right? This is a geometric series as well. Every time we get to the next term, we multiply by -1/2, right? 8 times -1/2 is where, I suppose really the easier way is just divide the next term by the previous term. -4 divided by 8 is -1/2. 2 divided by -4 is -1/2. -1 divided by 2 is negative, right? Every time it's -1/2. So this is definitely equal to the first term divided by 1 minus the ratio, which is going to be 8 over 3/2, which is 8 times 2/3, which is 16/3. But the idea here is that this applies whether or not the number, for any number really, for any number that's between 1 and -1. So what I'm trying to say in a lot of words is the following. If you look at this geometric series, 1 plus x squared plus x cubed, and so on, which we could definitely write as this equal to the sum from n equals 0 to infinity of x to the n. Well, we know how to add up a geometric series as long as the ratio is between 1 and -1. So our ratio here is x, right? Every term is x times the previous term. 1 times x is x, x times x is x squared, x squared times x is x cubed. And so the ratio is x. This is going to converge to the first term over 1 minus the ratio as long as our ratio is between 1 and -1, or as long as the absolute value of x is less than 1. So what we're actually saying here, right, is that this function can be expressed as this infinite series as long as x is between -1 and 1. Or in other ways is that this series from n equals 1 to infinity, x to the n, I'm going to write it in this longer way. This converges to 1 over 1 minus x on the interval of convergence. Which for this example is -1 to 1, or x between -1 and 1. And we definitely don't include the endpoints because we know that if x was 1, 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 diverges to infinity. And also if x is -1, 1 plus -1 plus -1 plus -1 plus 1 plus -1 diverges because it keeps going back and forth between 1 and 0. So I feel like that's kind of not the direction I want to go in just yet. But that's kind of the big idea. So a power series is kind of any series that you can write as, I feel like I'm lacking the right word here. Let me take one quick look so I make sure I don't say something super dumb. 1 second, sorry. I feel like there's a specific word I am lacking. No? Okay. I guess I'm not. So a power series just looks like this. A power series has this form. Sum from n equals 0 to infinity of some coefficient, which depends on what term we're at, times x to the n. This would be a power series centered at about 0. And then you can also write it as the sum from n equals 0 to infinity of some coefficient times x minus a to the n. And this one is centered about a. But the real kind of idea is just that the power series here, right? It's just a bunch of coefficients times x to the power. It's C0 plus C1 times x plus C2 times x squared plus C3 times x cubed, and so on forever. Now, the idea here is that we can use a power series to express a function. And sometimes this is super useful. Why might this be useful, you ask? Well, let me tell you a couple examples. But we're going to work back our way around to, but I'll say this. Here are two kind of well-known examples. Sine of x squared and e to the negative x squared. Both of these are functions that can be expressed with a power series. We might also say they can be expressed as a Taylor series or a Mcfarlane series, because the Taylor and Mcfarlane series are both examples of power series, just with a more specific format. And most series we encounter, most power series we encounter are going to be Taylor or Mcfarlane, so that's fine. But the reason this is nice is because there we can write, and we'll see this in a minute, we can write sine of x squared. I'm not going to say how exactly, but there's some way to write this as something, some constant, plus some constant times x, plus some constant times x squared, and so on and so on. And here's the thing. This function can't be integrated. Neither can this. We definitely are capable of integrating that. So one nice thing about power series is that you can use a power series approximation to then integrate something that we couldn't have integrated before. So that's kind of nice. That is a useful thing about power series. Sorry, let me see here. So I'm trying to kind of see about the way we want to go. Yeah, let's go this way. I just don't want to do that yet. Sure. So yeah. Let's look at some examples first, and then we'll kind of roll back around to. So we just eventually want to be able to say, like, how do you take a function and write it as a power series? And so far, here's what we've got. We know that we can write 1 over 1 minus x as the power series. 1 plus x squared plus x cubed. And again, I got bit by a mosquito yesterday. It's not the best. This is as long as the absolute value of x is less than 1. Right? This is definitely not true if x is 2. 1 over 1 minus 2, which is negative 1, does not equal 1 plus 2 plus 4 plus 8, et cetera, et cetera, et cetera. So only true for the interval of convergence. Yeah. So yeah, let's go this way first. So let's say we had this series. The sum from n equals 1 to infinity of x minus 3 to the n power over n to the 4th times 2 to the n plus 1. I want to find the interval and the radius of convergence. Okay. With almost without a doubt, when you're given a power series like this and asked to find the interval of convergence or the radius of convergence, they're very related to each other. You're always going to be using the ratio test. So remember the ratio test. The ratio test says that you take the limit of the an plus 1 term over the an term. If that limit is less than 1, then the thing converges. So we're going to do that. We're going to take the limit, as n goes to infinity, of the an plus 1 term, which is x minus 3 to the n plus 1 over n plus 1 to the 4th times 2 to the n plus 1 plus 1, and divided by the an term. So I'm not going to really divide by this, I'm going to multiply by the reciprocal. So times the reciprocal, so n to the 4th times 2 to the n plus 1 over x minus 3 to the n. And here's where we actually do need the absolute values. Because x could be anything. We want this limit. Eventually, we're going to say this limit has to be less than 1 so that this converges. Okay, well, let's simplify this. X minus 3 to the n plus 1 divided by x minus 3 to the n is just x minus 3. So I'm going to need x minus 3. And actually, x minus 3 is going to be the only thing that actually needs to be in the absolute value, because everything else has n's in it, which does not. 2 to the n plus 1 divided by 2 to the n plus 2. All of those 2's cancel except for one of them. So I've got a 1/2. And then finally, n to the 4th over n plus 1 to the 4th. Okay, as n goes to infinity, this doesn't care, this doesn't care, and the limit of this is 1. So this is equal to absolute value of x minus 3 times 1/2 times 1. And now we know for convergence that that limit has to be less than 1. So now we're going to solve for x. A couple ways to think about this. If you want to find just the radius, all you have to do is get to the place where you have x without any coefficient by itself. So if I multiply both sides by 2 and say the opposite value of x minus 3 is less than 2, that's my radius right there. If you have the opposite value of x plus or minus something less than the number, that number is your radius. I don't really like to think of it that way, but that is one way to do it. If I want to find the interval, I'm going to write, okay, well, if x minus 3 and absolute value is less than 2, that means x minus 3 is less than 2, bigger than negative 2. And I'm going to add 3 to all sides and get that 1 is less than x is less than 5. I'm not quite done. My interval of, so here's what I know. I know that x is between 1 and 5. This limit is less than 1. If I know that if x is bigger than 5 or less than less than 1, I'm going to get divergence, right? If x was, say, like 6 minus 3 is 3, 3 divided by 2 is 3 halves, and that's bigger than 1. And we know that if the limit of the ratio test is bigger than 1, then we get divergence. So now let me ask you guys a very important question, which you might know the answer to. I don't know. So I'm trying to close a few things here. So what if this limit were equal to 1? What if x was actually equal to 5? What do we know? We know nothing, right? The ratio test says if the limit is bigger than 1, you get divergence. If the limit is less than 1, you get convergence. If the limit is equal to 1. So here's what I'm trying to point out. We know that this power series converges if x is between 1 and 5, which means we also know the radius, because the radius is just half of this length, right? I would say from 1 to 5 is the diameter of the interval of convergence, which has a length of 5 minus 1, which is 4. And then the radius of convergence is half of that. So the radius of convergence is 2. The interval of convergence is from 1 to 5, but we have to go back and determine if it's actually convergent at the endpoints. So we need to check 1 and 5. Now, it's actually not terrible to check either of those. So if I plug in x equal to, let's say, 5. So if x is 5, I'm going to plug in 5. I'm not going to write the limit, the lower and upward one here. I'm just going to write 5. So 5 minus 3 is 2 to the n over n to the 4th times 2 to the n plus 1. That's equal to the sum. And cancel out of 2s. That's going to be 1 over 2 n to the 4th. That converges. We know it converges. I can bring out the 1/2, and then it's just a p series. So this converges. What about x equal to 1? So then if I plug in x equal to 1, 1 minus 3 is negative 2 to the n. So now I've got the sum of negative 2 to the n over n to the 4th. And I'm going to break up this 2 to the n as 2 times 2. So I'm going to break up 2 to the n plus 1 as 2 times 2 to the n. So then negative 2 to the n over 2 to the n simplifies to negative 1 to the n. So this is equal to the sum of negative 1 to the n over 2 times n to the 4th. You have 2 options here. Probably more than that, actually. One option is to show this converges by the alternating series test. That's the dumb option. Better option, say this converges because it's absolutely convergent, because look, we already said the absolute value of it converged. So this converges as well. Absolutely convergent. So our interval of convergence here is bracket 1 to bracket 5. But here's the real story. The real story is that we always have to check both endpoints. Sometimes they both converge, sometimes neither converges, sometimes one converges and one doesn't. So you always, always, always have to check both endpoints if you're talking about finding the interval of convergence. If your teacher is kind, I would not be kind in this situation. I would definitely ask them for the interval. But if they're feeling like not asking you to do that much work, they might just ask you for the radius. And the radius is just however long this is divided by 2. Doesn't matter if the endpoints are included or not. All right, let's look at a couple other examples of this. And then where are we at time-wise? Okay. Really? That's what we got? Let me see this. What's the OC? Sorry, it's the IOC, the interval of convergence. And then this is the ROC, the radius of convergence. Yeah, that's a very, at least I think it's a fairly typical abbreviation. I don't want to go back to that just yet. Yeah, okay. I just want to give you guys a couple more of these interval convergence problems because I think they're worth looking at a tiny bit more. Not you yet. Okay, sorry. I think that's what I want to check. Yeah, we can do this. Okay, sure, that's fun. Fun, right? You know. And then we'll roll back around to this, which is kind of the more important part. More important being a suspect here. Ooh, that could be interesting. Let's take a look at that one. Yeah. I want to know what's the interval of convergence for the sum from, what do we got here? N equals 1 to infinity. I'm going to change this around a little bit. X plus 2 to the nth power over 4 to the n plus 2 times the square root of n. Yeah, that seems reasonable-ish. Again, if we're talking about interval convergence, we're talking about ratio test. So ratio test, we want the limit as n goes to infinity of the absolute value of the an plus 1 over an to be less than 1. So that's going to be the limit as n goes to infinity of, okay, this with an n plus 1, so I'm going to have x plus 2 to the n plus 1 over 4 to the n plus 1 plus 2, so 4 to the n plus 3. And then the square root of n plus 1 times, or divided by an, which is times the reciprocal. So times the reciprocal of this, which is going to be 4 to the n plus 2 times the square root of n divided by x plus 2 to the n in absolute value. Okay, simplify. So x plus 2 to the n plus 1 divided by x to the n is just going to be x plus 2. And then 4 to the n plus 2 divided by 4 to the n plus 3 is going to be 1 over 4. And then the square root of n over the square root of n plus 1 is, you can either write it as the square root of n over the square root of n plus 1, or you could put that as 1 square root of n over n plus 1. And as you will often see with these problems, with any kind of ratio test problems, any kind of just powers of n, when you put them together, almost always have a limit of 1, right? N over n plus 1 goes to 1, and the square root of 1 is 1. So you're going to get the absolute value of x plus 2 divided by 4. And we want that to be less than 1, because that's when the ratio test shows convergence. So that means we want the absolute value of x plus 2 to be less than 4, which means we want x plus 2 to be between 4 and negative 4. And then we subtract 2 from every side, and we get x is between negative 6 and positive 2. Our length of convergence is 8, from negative 6 to 2. Our radius of convergence is half of 8, which is 4. And then our interval of convergence is negative 6 to 2, but we don't know about the endpoints. So let's check 2. So yeah, we plug in x equal to 2, we get the sum from n. You don't need to write the n equals 1 to infinity part. That's not super important. So n is 2, I get 4 to the n over 4 to the n plus 2 times the square root of n. The 4 to the n over 4 to the n plus 2, we can cancel out the 4 to the n's, and I'm left with a 4 squared in the denominator, which is equal to the sum of 1 over 4 squared times the square root of n. That 1/16 is not important, doesn't really matter, but the 1 over root n is divergent. It's a p series with p equal to 1/2. So this diverges when x is equal to 2. On the other hand, when x is negative 6, we're going to get, usually it's the difference is when you plug in one versus plugging in the other, is you get the thing to the n versus the negative of the thing to the n. So when I plugged in 2, I got 4 to the n. When I plugged in negative 6, I'm going to get negative 4 to the n. So I'm going to get the sum, negative 4 to the n. And in the denominator, I'm going to write 4 squared times 4 to the n times the square root of n. Hopefully you guys can see this okay. Negative 4 to the n over 4 to the n is negative 1 to the n. So this is the sum. Let's write it over here. I'm going to bring out the 1/16, and it's the sum of negative 1 to the n over the square root of n. Now, I don't want to show all the work for this because it's a pain, but typically when you get to here, you're like, oh, well, this is convergent. It's an alternate, so I'm just going to say this converges by the alternating series test. It's definitely alternating. right? The non-alternating terms are positive, the limit's 0, and the terms are decreasing. So this one, the interval of convergence would be -6 inclusive all the way to +2 exclusive. Once again, reinforcing the idea that we actually have to check the endpoints. Yeah, let me do 2 more of these and then we'll move on to something else. I mean, not something else, the same thing, but you know, same thing but different. Just a lot of math. It's the same, but it's different. Okay. Let me see. I've got some examples here. Sure. All right. So let's look at this one, which I feel like is going to be not super well. Yeah, it'll be fine. Let's look at the sum from n equals 1. Yeah, from n equals 1 to infinity of n factorial times x minus 4 to the n over 2 to the n times n cubed. All right, again, kind of boring. I mean, not boring, but it's repetitive, right? Maybe it's boring too, I don't know. It's definitely repetitive. You're almost always 100% of the time using the ratio test if you're being asked about the interval of convergence / radius of convergence. All right, so I do the limit here. Let's see, I'm going to get n plus 1 factorial, x minus 4 to the n plus 1 over 2 to the n plus 1 times n plus 1 cubed times the reciprocal of that. And we know how things are going to go. We know that the 2 to the n over 2 to the n plus 1 is going to leave us with a 1/2. We know that the n cubed over n plus 1 cubed, they're just going to go together. You can write it as n over n plus 1 cubed. We know that the n plus 1 factorial over n factorial is going to leave us with an n plus 1, which is kind of interesting. And then we know that the x's have to stay in the opposite values to the very end. The x minus 4 to the n plus 1 over x minus 4 to the n is just going to give us an x minus 4. Okay, now this one's kind of interesting. In fact, this is might have been one where I shouldn't have written the n over n plus 1 all cubed. So I'm going to rewrite this as n cubed. I mean, it's fine, but it's going to be easier to see what's happening if I write it like this. So we got n cubed over n plus 1 cubed. I can cancel one of these n plus 1s. So now look what's happening. I've got a limit where the degree on top is larger than the degree on the bottom, which means the limit is equal to what? This limit is equal to anybody? Infinity, which is definitely bigger than 1. Now, there's more to say here than just the limit to infinity. So if the limit to infinity, that means that this diverges. This diverges all the time with one exception. Can anybody think of the value of x that would make it so that this limit was not infinity? I'll give you a second to type in your possible answers in the chat. I know there's only like 4 of you. Any guesses? It's a very good guess. Yeah. So right, if x is equal to 4, then 4 minus 4 is 0. 0 times all this stuff is 0 before you take the limit, but then the limit of 0 is 0. So this is equal to infinity except when x is equal to 4. The limit is 0 when x is 4. 0 is less than 1, so this series converges. So the interval of convergence is kind of dumb to say here. The interval of convergence is, I'm going to write it in the wrong way, from 4 to 4. We would really just say that it converges at 4. So there's only one place where this converges. And this is always true. A power series will always converge at its center. So the center of this is 4, just like the center of this was -2, right? The center is always literally the center, right? The middle of -6 and 2 is -2. It's also the number that if you plug it in for x, you end up getting 0 to the nth power, or 0 right in there. So right, you're just going to add up a bunch of zeros, which is going to be 0. So a power series always converges at the center. Sometimes that's the only place it converges, like in this example. So here the interval of convergence is just the 1.4, and the radius of convergence is 0. Right, there is no length to the interval, just 1 point. And then, yeah, we can do one more. Go like this. Yeah. So the 3 kind of options for your radius of convergence are that it's a regular number, like 4 or 2 or a half, or it could be 0 if your interval just has 1 point in it. And every interval of convergence has to have at least 1 point, always a center of hanging up. Okay, and then the other option, which we're about to see here, is that the interval of convergence can actually be infinite. And let me just give you a real quick example. This is kind of a classic example that we'll come back to in a moment here. Let's say I have the sum from n equals 0 to infinity of x to the n over n factorial. This is a very famous power series. I will remind everybody that 0 factorial is equal to 1. Sorry, there's like gross stuff in my nails. You know, it's gross to like pick on my nails, but like this black dust in my nails is disgusting. I can't let it stay in there. It's terrible. Okay. It's not too awful anymore. It's kind of awful still. Sorry. Okay. I'll have to live with it. So this is equal to, right, x to the 0 over 0 factorial plus x over 1 factorial plus x squared over 2 factorial, and so on. And to find the interval of convergence, use the ratio test, limit n goes to infinity, x to the n plus 1 over n plus 1 factorial, divided by that times the reciprocal. And here you guys, I think, can see that, right? I'm going to get the limit as n goes to infinity. X to the n plus 1 over x to the n is just x. N factorial over n plus 1 factorial gives you an x plus 1 in the denominator. And no matter what constant term x is, a constant divided by something that's getting infinitely large is going to be 0, which is less than 1. So here, the interval of convergence is everything. And we say the radius of convergence is infinity. So those are your 3 options. Your radius can be 0, your radius can be infinite, or your radius can be some finite number in between 0 and infinity. All right. Let me back up a little bit here. Maybe not back up, but go back in a different direction. Where'd you go? Sorry, I have a whole thing. Yeah. So back to power series, because there is kind of some tricky stuff that you want to know about. Tricky and tricky. Yeah. So we're going to talk, probably not today, but definitely on Thursday, about Taylor and Mcfarlane series, about essentially how to find a power series for a function. This can get very technical. There's some small details. There's some like really wacky functions where you can find the power series, but it's technically not. There's some weirdness that we're not going to sweat too much. But we're going to use this fact a lot. 1 over 1 minus x is equal to 1 plus x squared, and so on and so on. As long as x is between -1 and 1. So here's another, so we're going to exploit this fact, is what I'm really trying to say. What if I want to write 1 over 1 plus x as a power series? Well, I'm always trying to make it look like 1 over 1 minus x, or 1 over 1 minus something. So I'm write this as 1 over 1 minus negative x. And essentially negative x is taking the place of positive x. So I can write this as 1 plus negative x squared, and so on. I can write this as the sum from n equals 0 to infinity of negative x to the n. Or if I don't like writing it that way, some people prefer, I could write it as the sum from n equals 0 to infinity of negative 1 to the n times x to the n. And this also converges for the same interval of convergence, because it converges if our ratio, right? Again, we've got a ratio here, it's negative x. This converges as long as our ratio is between 1 and negative 1, which is the same as if x is between negative 1 and 1. Cool, we just found the power series for 1 over 1 plus x. It's 1 minus x plus x squared minus x cubed plus x to the fourth, et cetera, et cetera, et cetera. But there's all kinds of tricks we can play. Like, what if I want to find the geometric series for x squared over 1 minus x cubed? Well, again, I'm always trying to get to this to look like 1 over 1 minus something is what I want. So here's what I'm going to do. I'm going to write this as x squared times 1 over 1 minus x cubed. So here in this one, x cubed is playing the role of the ratio. I'm going to erase some of this so I can. So this is equal to x squared times 1 plus x cubed plus x cubed squared plus x cubed cubed. I don't think you really need to write this step. We can write this as x squared times the sum from n equals 0 to infinity. Notice that most of these are starting at 0, so I can get the 1 as my first term here, of x cubed to the nth power. Now check this out. Thing 1, x cubed to the n is just x to the 3n. So this is x to the 3n, and then this x squared can come inside. Right? X squared isn't changing depending on what n is. So I can write this as the sum from n equals 0 to infinity of x squared times x to the 3n. I can add those powers and say it's x to the 3n plus 2. I just found the power series, centered at 0 for x squared over 1 minus x cubed. And the radius of convergence, well, here I need this to be between 1 and negative 1. So I need x cubed to be between 1 and negative 1. Well, that's still the same interval as before, but x is between 1 and negative 1. Kind of neat. Okay, and then there's some other tricks we can employ, like the following. So basically, there's one other example I should show you guys. But basically, the big idea so far is to write something as 1 over 1 minus some ratio r. Here's one more example. This one's a little trickier. What if I had, sure, let's make it 1 over, let's not make it super complicated, 2 minus x. I'm so close to 1 over 1 minus r. I have a 2 here. Now, there's 2 ways of doing this. One is definitely better. It really is, and it's the book way. So here's the way the book would have you do it, which I think is also the best way. It's 1 over, factor out of 2. Like that. There are other ways. It is also certainly an option. You could write it as 1 over 1 minus x minus 1. If that would also technically work. Right? Because that's a negative x, and a 1 minus a minus 1 is a positive 2. Here's the reason why we pick this and not this. This has 2 things going for it. One, centered at 0, which is in a vacuum preferable. But more importantly, this one actually has a larger interval of convergence than this one. And if we ever have a choice, we usually would prefer to pick the expression that converges for more values of x than the expression that converges for less value of x. So we're going to do it like this, not like this, even though this is the way I would generally think of doing it. So let's write this as, I'm going to factor out the 1/2. I've got 1 over 1 minus my ratio. Well, great, I know how to do that. That's going to be 1/2 times, I'm just going to go straight to writing it as the sum, right? We know that 1 over 1 minus r is the sum from n equals 0 to infinity of r to the n. So that's going to be the sum from n equals 0 to infinity of x over 2 to the n. Our ratio is x over 2, so we know this converges for x over 2 in absolute value less than 1. There's no worry about checking the endpoints here, because unlike those previous problems we were doing, we're using the ratio test. This is actually a geometric series, right? It's just the same thing, right? Multiplied by x over 2 each term. So we just have to be strictly between 1 and -1. No worries about the endpoints. So here you can multiply this by 2 and say that the absolute value of x is less than 2, or that x is between 2. That's definitely a larger interval of convergence than we would have gotten if we'd done it this way, which is cool. Some people might rewrite this. Some people might bring the 1/2 in and write this as the sum from n equals 0 to infinity of x to the n over 2 to the n plus 1. That's a typical thing to do here. This is our main trick. This is our main plan of attack. If someone says, here's a function, and it has vaguely looks like this, your job, your goal is to write it as 1 over 1 minus something. And then deal with the remaining extra parts afterwards. Like if there's a 1/2 out here, multiply the whole thing by 1/2. Or if there's an x squared on top, bring out the x squared and then multiply it back through at the end. We have 2 other tricks that are kind of the same trick, just in reverse of each other. So let me show you these 2 other tricks. And then I will have to go because I have office hours at 3. And I kind of need to use the bathroom before I have office hours at 3. Yeah, so Thursday we'll get to talking about Taylor and Mcfarlane series, which is just a more well-defined way of saying, here's a function, I would like the series for it. Instead of trying to use all these tricks, although we're still going to use these tricks, we say, well, here's the way you actually do it so that you get it right every time, no matter what, as long as it exists. But let's say I wanted to find the series for the natural log of 1 plus x. Well, that does not look like 1 over 1 plus x. But you know it does, or 1 over 1 minus x, but you know it does look like that? The derivative. So I know that the derivative of the natural log of 1 plus x is 1 over 1 plus x. And I know that 1 over 1 plus x, we did before, right? It's 1 over 1 minus x. That's equal to the sum from n equals 0 to infinity of negative x to the n. Or negative 1 to the n times x. In fact, this is definitely, when you start using derivatives and integrals, it's definitely the case where you actually want to separate this. And it is in our interest to certainly write this as the sum from n equals 0 to infinity of negative 1 to the n times x to the n. Here's why. The derivative of natural log of x is equal to 1 over 1 plus x. So that means that the natural log of 1 plus x is equal to the integral of 1 over 1 plus x. But I'm going to write 1 over 1 plus x as this series. So I can write this as the integral of all this. The sum from n equals 0 to infinity of negative 1 to the n times x to the n dx. Okay, so I'm going to integrate with respect to x. The negative 1 to the n doesn't matter, right? There's no x's there. Basically, what we really end up saying is typically the integral can pass through the sum, and you can write this as the sum from n equals 0 to infinity of negative 1 to the n times the integral of x to the n dx. But the integral of x to the n is just x to the n plus 1 over n plus 1. So this is equal to the sum from n equals 0 to infinity of negative 1 to the n times x to the n plus 1 over n plus 1. which is kind of cool. Now, here's the thing. People don't write it this way usually. People often re-index this so that you can start at 1. So instead of starting from n equals 0 to infinity, you like to start at, I'm going to write it using m just to kind of show how we're re-indexing. I'm going to say that m is equal to n plus 1. So if m is equal to n plus 1, if we start at n equals 0, in fact, let me write it down. If we start at n equals 0, well, if n equals 0, m is 1. If n equals infinity, m is infinity plus 1, which is also infinity, by the way. And then negative 1 to the n is going to become negative 1 to the, well, n is m minus 1. And x to the m over m. People often rewrite it this way. People often actually write it as the sum from n equals 1 to infinity of negative 1 to the n minus 1 over times x to the n over n. Alternatively, if you don't like doing this integral of the sum, you can actually just write out the terms as well. Right? You can say that, oh, the natural log of 1 plus x is the integral of, well, 1 over 1 plus x is, right, this here, which was 1 minus x plus x squared minus x cubed, etc. So you can say, oh, it's the integral of 1 minus x plus x squared minus x cubed, etc. And then you can actually integrate that and say, oh, look, that's equal to the integral of 1x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, etc. But then we can say, oh, well, look, that's just the sum from n equals 1 to infinity of x to the n over n, and then we alternate signs. That's another way you could have gotten there without having to do it this way. I feel like there's something else I want to point out here. Oh, yeah. So I'm going to say this now, and I guess we'll talk about it next time. No, I can talk about it. So it's worth pointing out that whenever you differentiate, which we didn't do here, or integrate a power series, right? We integrated the power series of 1 over 1 plus x. Now that does mean that the interval of convergence could change, right? Because unlike before, x to the n over n is not actually geometric, right? Negative 1 to the n times x to the n is certainly geometric. Every time we multiply by the same thing, negative x. Here, that's not the case. But here's what's great. Whether you have integrated your power series to get another power series or differentiated your power series to get another power series, the radius of convergence actually doesn't change. Super cool. We can look at this example just to show you. So if I actually look at this, right? So I have the natural log of 1 plus x equal to this. We know for the previous series, before we integrated it, we know that the series of 1 over 1 plus x, which is negative x again, we know the interval of convergence there is from negative 1 to 1. I'm going to show you that it's the same for this one by using the ratio test. So ratio test, limit is n goes to infinity of x to the n plus 1 over n plus 1 times n over x to the n. Well, the limit of n over n plus 1 is just 1. X to the n plus 1 over x to the n is just x. So this is equal to the opposite value of x. We want to be less than 1 for convergence. So here's the great thing. Whether you integrate or differentiate, radius of convergence and the center are both the same. So just like before, this converges if x is between 1 and negative 1. Here's the not great news. It is not true necessarily that we do not include the endpoints. We don't know if it converges for x equals 1 or negative 1 without checking. Right? Before, since it was geometric, we knew for sure, oh, x can't be 1 or negative 1, because 1 to the n added together is just going to be 1, and negative 1 to the n added together alternates back and forth between 1 and 0. But here, for this one, it might converge for one of these. In fact, it definitely does. If x is equal to 1, you have the alternating harmonic series. So it definitely does converge if x is equal to 1. If x is equal to -1, you do not, and here's why. So x is equal to -1, we end up getting the sum from n equals 1 to infinity of -1 to the n minus 1 times -1 to the n over n. -1 to the n minus 1 times -1 to the n, that's the sum of -1 to the 2n minus 1 over n. And here's the thing. No matter what n is, 2n minus 1 is odd, and -1 to an odd power is always negative. So this is really just equal to the sum of -1 over n, but that's just the negative harmonic series, right? You can just factor out the -1. That's the harmonic series that diverges, right? It's not the alternating harmonic series when x is equal to 1. When x is equal to 1, you just get -1 to the n minus 1, which it does alternate signs. So this one, so again, we're back in the situation of checking the endpoints. So this one converges on the interval of convergence, which is -1 to 1 inclusive of 1, which is neat. I should